All right, so now let's compare strength of bases. Very similar. If I have this equation here, a base should be a particle that can pick up or accept hydrogen from the solution. So if I compare products to reactants, this guy here would be labeled as a base. That's why he's just listed as B. He's a particle that can pick up hydrogen. Now again, if we want this thing to go in reverse, this guy here needs to lose that hydrogen. So we're going to call him the conjugate acid. It's the pair of the base. Acids and bases come in pairs, and the conjugates differ by just a hydrogen ion. And then I can do the same thing with water. Again, it feels kind of naughty to label water as an acid or a base, but if water is in solution with something else, it can act as a hydrogen donor or a hydrogen acceptor. So I see I have H2O. On the product side, it's OH. This is the hydrogen donor. Water is acting like an acid. But then if this OH particle wants to go in reverse, then he has to pick up a hydrogen. We would call him the conjugate base. And obviously OH is always the sign of a base, so that makes sense. When I do my equilibrium expression, then we're going to call it Kb, the base dissociation constant. It's still products over reactants, but again, notice that we have omitted the liquid water. No liquid water, because we do not include pure liquids or solids in our equilibrium expressions. So a lot of the same rules apply that did to acids. Strong bases really favor the forward. They dissociate nearly 100%. Almost all of the original bases dissociated. Well, if you have primarily ions, products, and you go products over reactants, you should get a really large K value. It says a strong base produces a weak conjugate acid. So again, now if this thing really favors the forward, almost 100%, like do we go in reverse? Maybe not at all. Then this guy here, this conjugate acid, this must be really weak. That guy really doesn't have a good chance of losing his hydrogen and sending this thing in reverse. Common strong bases then. Soluble hydroxides. That's usually what I'll say. In general, soluble hydroxides. Alkali metals like potassium and sodium, those are all soluble hydroxides. Some alkaline earth metals are relatively soluble hydroxide compounds. The best examples are probably sodium hydroxide, potassium hydroxide. I mean, like calcium hydroxide is marginally soluble. Sometimes we'll call that a relatively strong base. But if we wanted to be specific, we'd look at the K value. If I have a small K value, something times 10 to the negative something power, that's when I'm starting to think this base is more weak. Where do I favor the forward? Maybe not a lot. Maybe only 1 out of 100 molecules actually goes forward to produce ions. So the Kb value is small. It's mostly neutral particles, not a lot of product ions, not a lot of hydroxide in particular. It says a weak base dissociates only to a small extent in solution. And the conjugate acid of a weak base is actually a stronger acid than the water. So if I go back to this original expression, now in a weak base, this thing favors the reverse. So now this must be more likely to lose hydrogen than water. That conjugate acid must be a stronger acid than the original water, more likely to produce hydrogen ions. Common weak bases, like ammonia is probably the best example. Amine compounds. Amine means nitrogen. These are usually big long chains of carbon. So you might have like carbon, carbon. They're surrounded with hydrogens. Hydrogen, hydrogen. And then maybe some more hydrogens. And then you'll have a nitrogen. And then to fill out the nitrogen, there's always the lone pair. So here's my lone pair. And then there'd be like 2 hydrogens. This thing here is an amine group. Amine means nitrogen. And we kind of looked at the structure of nitrogen compounds like ammonia, would just be that NH3. On top of the nitrogen is a lone pair of electrons, which makes that region very negative. Plus, the nitrogen has a high electronegativity, so the electrons that are bonded between nitrogen and hydrogen are drawn toward the nitrogen, again, making that region very negative. Well, then there's a good chance that the negative nitrogen would be attracted to hydrogen, especially like from water molecules. Rips the hydrogen right off the water, kind of like this example here. One of these hydrogen ions gets removed, and you're left with OH, the sign of a base. So again, I usually think of nitrogen compounds as being good bases, weak bases. Sodium bicarbonate. We'll kind of talk about this guy. The bicarbonate ion is HCO3, -1. In solution, this guy can remove hydrogen. It could react with hydrogen and form that neutral H2CO3. It could act like a weak base. However, let's look at this guy a little more. Along with water as another example, there are some compounds that can act as either acid or base. We call them amphoteric, or sometimes you might see the word as amphiprotic, meaning that it can either gain a proton or lose a proton. And a proton is really the same as a hydrogen ion. Water is a great example. Water can go either way. We've kind of seen that. Water can actually self-ionize. If two water molecules collide and the hydrogen ends are both positive and the oxygen ends are both negative, there is the chance that they could transfer a hydrogen just between the two water molecules. You would form that hydronium ion, H3O plus 1, along with hydroxide. But we say that this is still a neutral solution. The H3O is always an acidic particle, the OH is a basic particle, but you're always going to get one of each. So there's always a balance between acidic particles and basic particles. So we still do say that water is neutral. Another example might be something like this guy. HCO3-, like that bicarbonate ion. That guy could go either way. In solution, he could produce hydrogen. He could go forward, release a hydrogen ion, and then be left as the CO3 carbonate. In that case, the bicarbonate ion is acting like an acid. It's removing hydrogen. It's, I should say, releasing hydrogen. But he could also go in the opposite direction. This guy, bicarbonate, could react with hydrogen in the solution and form this guy, H2CO3, which is just a weak acid. This is a very weak acid, carbonic acid. Which means then, does that dissociate? Not by much. So will it shift in reverse? To the smallest extent. But really then, we could say, in the first case, this guy is acting like an acid. In the second case, it's acting like a base. He does have the ability to pick up hydrogen from the solution. If you're removing hydrogen from the solution, you're acting like a base. So amphoteric, or sometimes again they'll call it amphiprotic, are particles that can go either way. They can act as acid or base. Water is a great example, but that bicarbonate is another good one. Okay, so one more K value. Kw is the dissociation constant for water. Since now we kind of know that water does have this ability to self-ionize. Water can form ions. But again, now look at the expression. This is in your AP packets. You don't have to memorize these. Actually, all of them. Ka, Kb, and Kw, they're in the packet. You just got to dig them out and know when to use them. It can be written either way. You could write the acidic particle as hydronium H3O+, or you can just write it as H+. Either way, it's the sign of an acidic particle. But notice too that if you go products over reactants, we do not include the pure water. It's just the products. The original pure water in the liquid phase does not get included in our KW expression. This guy, then, is in the AP packet. We'll make a little note. No water in the liquid phase. We do not include liquids and solids in our equilibrium expressions. Another thing that's given to you in the AP packet, you do not need to memorize this. Okay, so now from experimentation, we know that in a sample of water, you should find 1.0 times 10 to the negative 7th moles of hydrogen and 1.0 times 10 to the negative 7th moles of hydroxide per liter. That's just by how far forward this thing goes, not by much. I mean, those are very small numbers. 10 to the negative 7th, that's not a lot of hydrogen or hydroxide. If I have a beaker of water, it is primarily neutral water molecules. Does it self-ionize? Sure. Not a lot. Now again, they will notice, or note that this is at 25 degrees. Because if I do increase the temperature, that'll increase the production of ions. And so they'll usually say that at 25 degrees, the concentration of hydrogen and hydroxide in a sample of water was found to be 1 times 10 to the negative 7th. Which, like if you remember, do you remember like calculating pH, which we'll do very soon? pH is opposite log of the hydrogen ion, which is really just the opposite exponent of 10. So we would say the pH is 7. Oh, okay, well that kind of makes sense then. It's from experimentation that we get this number though. Okay, so now here's what we can do. We can calculate a value for a KW. In a neutral sample of water, all we got to do is plug this guy in then for both hydrogen and hydroxide. KW is this. It's a constant. KW is always 1.0 times 10 to the negative 14. It comes from experimental data. At 25 degrees, that just is the amount of hydrogen and hydroxide that you would find in a liter sample of water. The last thing that they will give you in the AP packet is this, which we will use shortly. If you know KW, which you will, that's a constant, 1 times 10 to the negative 14th, that should equal Ka times Kb. And you can apply this to all kinds of different solutions. If you have the Ka and you want the Kb, you can plug it into this equation. All you need to know is one or the other, and we'll always know the dissociation constant for water. So in the next couple chapters, in the next couple videos, we'll start using this. We'll figure out, like, okay, how can I use this KW to solve for a Ka or a Kb, one that might be missing.